14 kilometers. That's all that separates two entire continents. For nearly a century, engineers have imagined building the impossible, a bridge between Africa and Europe across the Strait of Gibraltar. Beneath those waters lies 900 meters of depth, 1,000 meters of unstable sediment, and a seismic zone violent enough to shatter any foundation ever conceived. The price tag is up to $30 billion. The ancient Greeks marked this strait as the edge of the known world. And what lies beyond that edge is a story that begins not with blueprints, but with a myth. What does it mean to stand at the edge of the known world? For ancient travelers, the Strait of Gibraltar was more than a stretch of water. It was a threshold, marked by two colossal sentinels, the Pillars of Hercules. According to Greek legend, Hercules himself tore open the mountains, splitting a single landmass and leaving behind a gateway between continents. On one side, the Rock of Gibraltar. On the other, Jebel Musa. Together, they formed the western boundary of civilization, a place where the familiar ended and the unknown began. Classical writers like Herodotus and Strabo describe this place in hushed tones, as if crossing it risked angering the gods. Roman poets called it the world's final frontier, a line no mortal should cross. Medieval maps painted the strait with flourishes of sea monsters and warnings. Beyond this point, there be dragons. The pillars appeared again and again, not just as rocks, but as symbols of human limits. For centuries, they stood unchallenged, a natural wall dividing not only Europe and Africa, but the possible from the impossible. Yet, even in those earliest stories, the strait was never just a barrier. It was also a promise. Merchants and sailors saw opportunity in its currents. Phoenician traders built ports on both shores, moving goods between worlds. Arab geographers mapped its tides, searching for safe passage. The myth of Hercules inspired generations to imagine what might lie beyond, and what it would take to bridge that gap. Cartographers of the Renaissance, drawing from both Greek and Arab sources, etched the pillars onto parchment as emblems of ambition and fear. The strait's narrowest point, only 14 kilometers, became a canvas for speculation. Could the continents be joined? Was it possible to tame the waters that had defied every empire before? The legend of the pillars echoed through the centuries, shaping the dreams of explorers and the ambitions of engineers. The strait was not just a place on a map, but a challenge written into the landscape. To cross it was to defy myth, to claim a victory over the very boundaries that defined the ancient world. Before any blueprint, before any calculation or cost estimate, the idea of a bridge across Gibraltar began here, in the mythic imagination, on the threshold where legend meets the limits of human effort. What does it take for an idea to leap from legend to blueprint? In 1930, a Spanish engineer named Alfonso Pena-Buff dared to sketch the unthinkable, a tunnel beneath the Strait of Gibraltar. His plan, submitted to the Ministry of Public Works, described a 14-kilometer rail tunnel, shielded from the crushing weight of the sea by steel and concrete. The technical drawings, tucked away in government archives, have yet to be digitized, but newspaper accounts from the era hint at the scale of his ambition, a project stretching beneath waters deeper than any tunnel then conceived, demanding technology that barely existed outside the dreams of Europe's boldest engineers. Pena-Buff's vision did not move beyond paper. Political uncertainty, economic hardship, and the daunting realities of the seabed consigned his proposal to the shelves. Yet the idea lingered, gathering momentum as the century advanced. By the late 1970s, Spain was emerging from dictatorship, Morocco was opening to global investment, and the two governments recognized a shared opportunity. In 1979, they signed a treaty that created a joint committee, the Comité Mixto Gibraltar Strait, tasked with exploring the feasibility of a fixed link. For the first time, the crossing was no longer a solitary dream. It became a matter for diplomats, engineers, and economists on both sides of the water. The committee's mandate was broad: evaluate both bridge and tunnel options, assess seismic risk, and confront the geological unknowns of the Camarines Sill. Their records, preserved in the Spanish Ministry of Transport archives, reveal a period of intense study. Technical memoranda from the early 1980s weighed the cost, complexity, and political sensitivities. Reports from the International Road Federation's 1980 conference in Nairobi show that optimism ran high. Engineers from Britain, France, Spain, and Morocco gathered to discuss how advances in tunnel boring machines and offshore construction might finally make the crossing possible. Behind the technical language, a new reality was forming. The Gibraltar crossing was no longer just a symbol. It was a test case for transcontinental cooperation. The committee's work established protocols for data sharing, environmental assessment, and risk management that would echo in later megaprojects. Every feasibility study, every diplomatic cable, every archival sketch brought the dream closer to reality, but also exposed the scale of the challenge. The strait's depths, seismic volatility, and shifting currents demanded solutions beyond anything attempted before. The groundwork laid by Pina Buff and the 1979 committee set the stage for a new era. The idea of bridging continents had moved from myth and lone visionaries to the realm of international mandate. Now the question was no longer just whether it could be imagined, but whether it could be built. The stage was set for modern engineering to confront the full force of the strait's natural power. What does it take to imagine a bridge that spans the limits of human possibility? The Strait of Gibraltar, only 14 kilometers wide at its narrowest, demands a structure that dwarfs every bridge ever built. The numbers alone seem to defy sense. A total length of 14 kilometers, with a main span stretching nearly 2 kilometers between two colossal towers. Each tower would rise 150 meters above the waves, taller than a 40-story building, standing sentinel over one of the world's busiest shipping lanes. But the dimensions are just the beginning. This crossing would hang above waters that churn with relentless winds. The design must withstand gusts reaching 70 miles per hour, winds strong enough to rattle the steel nerves of any engineer. For comparison, the Millau Viaduct in France, famed for its elegance and resilience, was tested in wind tunnels to survive similar gales. Yet the Gibraltar Bridge would face these conditions as routine, not exception. Every cable, every meter of deck would be shaped to slice through the air, using aerodynamic tricks borrowed from the world's most advanced bridges and refined through decades of wind tunnel trials. The deck itself must be more than a road. It is a living corridor, 35 meters wide, designed to carry 4 lanes of traffic and a high-speed rail line, enough to move 50,000 vehicles and 30,000 passengers each day. To keep the deck stable, engineers propose a fan of high-strength cables, each one made from carbon fiber reinforced polymer, lighter and more durable than steel. This material, first used in the Millau Viaduct, reduces weight by nearly a third and resists the relentless salt spray that corrodes ordinary metal. The cables and deck would be monitored by a web of fiber optic sensors, feeding real-time data to an AI platform trained to spot the earliest signs of fatigue or vibration. Even with these innovations, the bridge must clear a 70-meter high channel for ships, enough space for the world's largest tankers to pass beneath, day and night. The towers, planted on either side of the strait, must absorb the force of wind, the weight of the deck, and the constant vibration of traffic. Every element is pushed to its limit, each calculation a wager against the unknown. As one lead structural engineer put it, this is not just a bridge, it's an act of faith in our ability to master the elements. The geometry of this structure isn't just about numbers, it is a confrontation with the very forces that define the strait, wind, water, and the unyielding urge to connect two continents. Yet for all the precision above the surface, the greatest questions still lie hidden below, in the darkness of the seafloor, where geology and seismic risk threaten even the boldest design. How do you anchor a dream to the bottom of the sea? For engineers, the challenge of Gibraltar begins not with the wind or the waves, but with the hidden world beneath the surface, a landscape as formidable as any myth. The numbers alone are enough to give pause. The strait plunges to depths approaching 900 meters at the Cameronal sill, deeper than any bridge foundation attempted in human history. But depth is only the beginning. The seafloor here is not solid rock. Instead, it is a shifting column of sediment, over 1,000 meters of soft clays and sand, built up over millennia, lying between the water and the bedrock below. Core samples taken by marine geologists reveal a vertical tapestry of silt and mud, some layers barely compacted, others dense with ancient organic matter. One CPT core extracted at 850 meters depth showed less shear strength than wet concrete. In such conditions, even the heaviest pile would drift and tilt, unable to find purchase. Every meter deeper, the challenge multiplies. And then there is the threat that cannot be seen from the surface: seismic risk. The strait sits atop the restless boundary where the African and Eurasian plates grind past each other. Probabilistic seismic hazard models predict a peak ground acceleration of 0.35 g, enough to rattle even the most robust structures. The region's earthquake history is written in the scars of the seabed. Submarine landslides, triggered by distant tremors, have left buried scars hundreds of meters wide. Acoustic surveys show zones where sediment has slumped, shifting entire layers sideways in a single event. Seismic forces are constant and unseen. For a bridge, these forces pose existential questions. How do you design a foundation that can absorb not just the weight of steel and concrete, but the shock of a magnitude 8 earthquake? How do you build on a base that might liquefy and shift beneath your feet? The answer is not yet clear. Engineers debate anchored caissons post-tension to the bedrock, or hybrid systems that combine deep piles with flexible joints. Every solution faces the same reality. The strait's foundation is less a platform than a living, moving puzzle. A marine geologist standing on the deck of a research vessel can hold up a core sample and point to the fine layers of clay and silt, each one a record of ancient storms and slow-moving currents. But no core can guarantee stability. The only certainty is uncertainty, a hidden antagonist that haunts every calculation, every cost estimate, every leap of faith. The dream of bridging continents must first reckon with the deep, silent forces below. What does it cost to defy the boundaries of nature? The Gibraltar Bridge proposal carries a price tag that matches its audacity. The projected capital outlay stands between 25 billion and 30 billion US dollars, a sum that rivals the GDP of some nations. To translate vision into steel and concrete, the project demands nearly 5 million tons of materials. That is enough to build more than a dozen Golden Gate bridges, or to pave a highway from Madrid to Tangier twice over. The logistics of assembly are no less staggering. Each tower and deck segment must be fabricated with a precision that leaves no margin for error, then shipped and positioned above waters nearly 1 kilometer deep. The construction plan stretches across 15 years, with a target groundbreaking in 2030. Early phases focus on detailed geotechnical drilling and foundation work, followed by the slow rise of the towers and the intricate weaving of cables. Deck installation and rail integration fill the final years, culminating in a structure designed to last a century and a half. Financing a project of this scale requires more than deep pockets. A public-private partnership model is on the table, combining equity from international consortia, loans from the European Investment Bank, and sovereign bonds issued by both Spain and Morocco. Each milestone, including drilling, tower fabrication, and main span erection, unlocks further capital, but also exposes the project to the unpredictable tides of global finance and political will. The bridge is no longer just an engineering risk. It's a financial wager on the future of two continents. Who controls the gateway between Africa and Europe? The answer is anything but simple. At the heart of the strait stands Gibraltar, a British overseas territory claimed by Spain, braced against the winds of post-Brexit uncertainty. Every meter of proposed bridge or tunnel must pass through a thicket of sovereignty claims, security protocols, and shifting alliances. Diplomatic cables from Madrid, London, and Rabat reveal a persistent standoff. Spain insists on consultation over any fixed link, while the UK guards Gibraltar's autonomy with a watchful eye. Morocco, eager for economic gain, must navigate both European hesitancy and its own regional ambitions. The European Union, meanwhile, has drawn a hard line on migration and border control. Any fixed crossing would be more than a marvel of steel and concrete. It would become a front line in the struggle over who moves between continents. The European Union's border agency Frontex has demanded that the crossing be equipped with biometric checkpoints, automated identity scanners, and a digital monitoring grid capable of tracking every vehicle and passenger. These requirements are not negotiable, and the bridge or tunnel must function as a fortress as much as a thoroughfare. Gibraltar's own representatives warn that the territory cannot become a loophole in Europe's migration system. They point to the 2025 European Union directive mandating biometric entry-exit records at all external borders, a rule that would require the installation of advanced surveillance and data sharing systems, technologies that raise privacy concerns as well as logistical headaches. Policy analysts in Brussels describe the project as a legal minefield, where a single unresolved detail could halt progress for years. The result is a paradox. The physical gap between continents may be just 14 kilometers, but the political distance is measured in decades. Before a single foundation is poured, the project must clear a gauntlet of treaties, border regimes, and sovereignty debates. In the end, no amount of engineering ingenuity can bridge a divide that governments refuse to cross. Beneath the ancient meeting point of continents, the Gibraltar Tunnel would run 38 kilometers, nearly triple the length of its bridge counterpart, carving a silent path under the strait. At its deepest, the tunnel would plunge 475 meters below the sea, demanding a 40% premium over the bridge's cost. In exchange, it promises to move the equivalent of 50,000 vehicle passengers per day, immune to the surface's notorious windstorms, and cutting travel times dramatically. Tunnel engineers reference the Saykan and Channel tunnels as precedents, but Gibraltar's depth and seismic risks set it apart. Machines would need to withstand crushing pressure and unpredictable geology, while advanced safety systems, including ventilation, emergency exits, and fire controls would be pushed to new limits with every kilometer. Yet the greatest challenge may not be technical. The strait is a migration corridor for fin and humpback whales, their calls echoing through the water. Marine biologists warn that construction noise, even filtered by layers of rock, could disrupt navigation and breeding. Mitigation measures such as bubble curtains, seasonal work pauses, and real-time acoustic monitoring offer hope, but no guarantees. Above, the Pillars of Hercules guard a UNESCO heritage site, where any surface disturbance risks violating both law and legend. Every promise of speed and connection is weighed against the cost to a fragile world. The tunnel's legacy will be measured not just in engineering, but in the balance struck between progress and preservation. Today, the blueprint remains on paper, while currents churn above 1,000 meters of restless rock. As global migration and trade reshape continents, the dream of uniting Africa and Europe grows more urgent, yet more daunting. The strait still divides worlds, not just land. What we dare to build here will echo far beyond concrete and steel. Would you cross the line between continents? Share your thoughts below.